Hello, my name is Daniel Sank, and I'm a staff research scientist at Google. I work on quantum computing, specifically on superconducting microwave resonators, which can be used as the fundamental bits in a quantum computer. In this talk, I'll discuss a particular variant of a quantum bit, which is called the transmon, from the point of view of microwave circuits. Before we get started with the technical stuff, though, let me introduce the team. We are distributed over 3 sites. The experiment is centered in Santa Barbara, California, where our qubits are made, tested, and operated. And our theory and applications team is centered in Venice, California, where the theory of the physical devices is developed and near and long-term applications of quantum computing are investigated. Our cloud software team is centered in Seattle, Washington, where the software interface to talk to our hardware is built. The overall goal of the team is to build a fully error-corrected quantum computer, but we're also working on shorter-term applications as well. The team is rather intellectually diverse. We're made of physicists, chemists, electrical engineers, fabrication engineers, software engineers, and people from other disciplines too. Team members come both from academic and industrial backgrounds. And I have to say, it's the diverse set of colleagues and their backgrounds that's one of the things I most enjoy working with this team. Okay, so here's an outline of the talk. First, I'm going to give an introduction to quantum computing in general. Then I'm going to talk about microwave quantum bits, or qubits. So in that section of the talk, I'm going to try to explain how we take microwave resonators and turn them into quantum bits. Then we're going to talk a little bit about how we control our qubits. And finally, at the end, I'll talk about how we read out our qubits. Also, make sure to see Joe Barden's talk. This talk is largely an introduction to his. Okay, so let's start with quantum computing. The starting point to understand quantum computing is to understand computing in general from a physics point of view. So all information is fundamentally physical. Here's an example of 3 information processing devices, and for each one I've written down what the physical encoding of the information is. So to start on the left, we have an abacus, and in that case, the information is stored in the positions of the beads. We also have a DRAM circuit, where information is stored in the presence or absence of charge on the capacitors. And then, of course, we could also have an analog clock, where information is stored in the angle of the various hands. Now, each of these cases is based on physical principles that were already understood in the 1900s. These are all physical state machines. The kind of physics known in the 1900s is typically referred to as classical physics, but you see, since then we've learned new rules of physics called quantum mechanics, and in discovering those new rules, there's sort of an obvious question, which is, can we make information processing machines that leverage quantum mechanics to process information in new ways? In fact, we can. And we're going to show later in the talk, to some degree, how that's done. But before we get into the details, let's go a little further and understand what even could be the difference between classical information processors and quantum information processors. So first, let's start with a classical state machine, a deterministic classical state machine. So suppose this thing has 2 bits, as shown here. A 2-bit machine has 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. Now, we can line those up and store them in a vector. So this vector that I'm showing here has 4 elements, and when there's a 1 in the first slot, it means that our state machine is in the state 0, 0. If the 1 were in the 3rd slot, it would mean that the state machine is in state 1, 0. Now, of course, the state machine has to be in one state at a time, so at any point in time, this vector is going to only have a single 1, and the rest of the elements will be zeros. How would we represent a logic operation in this representation? Well, it turns out you can just use a matrix. So here is an example of a matrix representing a particular logic operation. And to understand how it works, we can go column by column. So recall that each column of a matrix tells you what that matrix does to each possible basis vector. So for example, if we were to act this matrix on the state 0, 0, there's a 1 in the slot for 0, 1, which means that this matrix sends the state 0, 0 to the state 0, 1. Or in other words, it sends the state vector with a 1 in the first slot to a state vector with a 1 only in the second slot. That's why the 1 is in the second row here. So similarly, this matrix sends the state 0, 1 to the state 1, 1, and so forth and so on. Of course, this matrix can only have a single 1 in each column because it has to deterministically send one state to one other state. So if we were to act this matrix on an input state, let's see what we would get. Well, if we start with a 0, 0, it sends us to 0, 1. And that's what I'm showing down here, where I plot the state of the computer versus time. If we act the same logic operation again, we can see that it sends the state 0, 1 to the state 1, 1. And that's what we show with the second arrow here. And so forth and so on. The deterministic state machine goes from one state to the next as we act logic operations on it. Now, suppose that we had either a random number generator or computer hardware that actually had randomness baked in. In this case, each element in our state vector could represent the probability that the computer is in that state. So for example, this state vector right here has a 1/2 probability to be in the state 0, 0, a 1/4 probability to be in the state 0, 1, and a 1/4 probability to be in the state 1, 1. Similarly, the logic operation matrices now are more complex because each one is now telling us the probability to go from one state to the next. So for example, this stochastic logic gate represented by this matrix would send the state 0, 0 with 1/2 probability to the state 1, 1, or excuse me, to the state 0, 1, or with 1/2 probability to the state 1, 1, and so forth and so on for the other input states. Now, of course, there can be more than one non-zero entry in each column now, but the sum of each column has to equal 1 because the probability to go somewhere from each input state has to be 1. Now, when we look at what happens to the input state 0, 0, if we act this particular logic operation several times in a row, we can see that the probability spreads out. In fact, we wind up with non-zero probability in every possible output state. You could ask, what's the probability that the output state is the third state 1, 0? And the way you would answer that question is that you would look at all possible pathways to get to that output state, and you would sum the probabilities. Here I'm showing in red the paths that lead to the output state 1, 0. Now, what about a quantum computer? Well, a quantum computer is just like the random or stochastic computer we described in the previous slide, with one difference. The elements of the logic operation matrices are now complex numbers. That's really the only difference. What happens when we allow this matrix to have complex numbers? Well, because they can be complex and in fact can be negative, what happens is that not only do probabilities add as we go through different paths here, but sometimes they subtract. So in fact, the sort of art of quantum computing is to choose and build logic operations in such a way that the probabilities add constructively to give us the correct output state for whatever algorithm we're trying to do, but add destructively for the incorrect outputs. So in this illustration, I've colored most of the output arrows here in a light blue to suggest that they're subtracting from each other and giving a 0 probability in the output, whereas the red ones add constructively and give us a large probability in the output. That's really the essence of quantum computing. You want to build a computer that's kind of like a random computer, except that the probabilities can be complex. And it turns out that quantum mechanics, the physical principles of quantum mechanics, tell us that this is actually possible to build in hardware, because fundamentally in nature, the sort of probabilities of the way things move around are actually represented by complex numbers. So that means that if we can build hardware that behaves quantum mechanically, then we should be able to build a computer that behaves in the way that we just discussed in this slide. Okay, so now an obvious question is, well, how do you make physical bits that actually have these complex valued amplitudes? Well, we'll get into more details as we go on, but the one thing that I really want to emphasize up front is what it is that we have to do to make something behave quantum mechanically. And it's all based in a fundamental key idea. In classical physics and in conventional computing, information can be copied. If there's a color wheel here and two people look at it, both of them can gain perfect information about the color wheel, represented here by the fact that they have the color wheel in their minds. However, in quantum mechanics, information cannot be copied. So what happens is if you have some information in the center here and two people look at it, the information is moved. So if the observer on the left sees the red part of the color wheel, then that information is gone and is now in their mind. Whereas the viewer on the right looks at the blue part of the color wheel, that information is on the right in their mind. And that information no longer persists in the center. And in particular, these two observers cannot share any of the quantum information represented by this color wheel. Okay, so that's a very esoteric idea. So now let's bring this down to the level of circuits so we can understand what we have to do to an electrical circuit in order to make it quantum. Let's start with something really simple, an LC resonator, as shown here on the left. Now, an LC resonator is normally made of a normal metal. And in a normal metal, as the electrons travel through, sometimes they go through uninterrupted, but sometimes they scatter. So this jagged red line here represents an electron that's bouncing off of the ions inside the metal. And when an electron scatters like this, it causes the ions to vibrate. It makes lattice vibrations in the wire, which is why you get Joule heating. Now, those lattice vibrations are waves. They're compression waves inside the solid. And the thing to notice here is that if a compression wave radiates away, that carries information about what the electrons were doing. So remember on the previous slide, we said that quantum information cannot be copied. Well, that means that if an electron scatters and sends off a wave, and that wave carries information about what the electrons were doing, then some of the quantum information about what was going on inside this wire, inside this LC resonator, is being carried away. And it's no longer available to others. For example, if we're doing an experiment with this LC resonator, some of the information has been gone and is not available to us. That means that as long as we have this phonon scattering, we will not be able to observe the quantum behavior of this resonator. So there's a simple solution. If we simply make the resonator out of a superconducting metal and cool it down, then the electrons no longer scatter and there's no more leakage of information away from this resonator. And if we do that, all of the physical information about the resonator remains in the resonator. It turns out that's all you have to do to make an electrical circuit behave quantum mechanically. You just cool it down, get rid of all the noise processes that were carrying away physical information, and that circuit really will behave quantum mechanically. To get our resonators superconducting, we put them inside dilution refrigerators. A dilution refrigerator uses helium as its working fluid and can get down to 20 millikelvin, which is colder than deep space. Superconductivity in aluminum, the metal that we use in our circuits, only requires cooling to about 1 Kelvin, but it's easier to keep the quantum states alive if we cool them down further to 20 millikelvin. Basically, the issue is that lower temperature suppresses some of the processes that steal the circuit's quantum information. The practical condition that you want to satisfy is that the temperature should be much less than Planck's constant times the resonator's resonance frequency divided by Boltzmann's constant, which for our 6 gigahertz resonators comes to about 0.3 Kelvin. So getting down to 20 millikelvin gives us about a factor of 10, which is nice and safe. Fortunately, commercial dilution refrigerators can get down to 20 millikelvin no problem. This is an image of a dilution refrigerator with its vacuum jacket removed, so you can see the insides, the insides of the refrigerator. They're separated into several stages. Each round copper plate here is a different temperature stage, with the bottom one getting down to the base temperature of 20 millikelvin. We run coaxial cables from room temperature through the various stages down to the sample, which is contained in this little package right here. And you can see some other interesting features. For example, this coiled piece of hardware right here is a heat exchanger that helps the liquid helium get down to the temperature that it needs to for cooling. Okay, now let's talk about how we actually take a microwave resonant circuit and make it behave like a quantum bit, or qubit. We're going to start with something we already understand. A classical LC resonator, shown here with an L and a C, driven by a voltage source, VD, through a resistor R, and coupled in through a capacitor, CD. Using Kirchhoff's laws, we can write down a second-order differential equation that describes this circuit. So here's that equation right here. I've written it in terms of capital phi, which is the flux through this inductor. You could do this in terms of the current in the inductor or the voltage on the capacitor, but it turns out that the flux is a particularly convenient variable to use in the quantum mechanical case. So this differential equation has four terms. There's the second order derivative of the flux here, which is sort of like the inertia. There's a damping term right here that depends on QD. QD is the quality factor of the resonator that it gets because of the drive. So there's the coupling capacitor CD and this resistance, and that gives you a loaded Q, which is given by this equation right here. So that Q shows up in a damping term. Then there's the restoring force term that has omega naught squared, where omega naught is the resonance frequency of the LC. And then we have the drive. So the drive depends on the time derivative of the drive voltage, VD, and then there's a ratio of the drive capacitor and the self-capacitance. Now, this second order differential equation is a bit hard to work with, but it turns out that if we go into the baseband, or what a physicist would call the rotating frame, things simplify quite a bit. So we take the flux, and we write it in terms of a phasor, phi, where we've taken out the time dependence e to the j omega t, where omega is a reference frequency or a carrier frequency. We do the same thing for the drive voltage. We write that in terms of a cosine and a sine at the carrier frequency, with the modulation functions I of t and q of t factored out. Doing that, we can write VD as the real part of a drive phasor, z of t, and the time dependence e to the j omega t. Now, once we've done that, this second order differential equation we got from Kirchhoff turns into a first order equation given here in the top right. So this equation has similar terms to the second order equation, but it's a bit simpler. So there's the drive term here that depends only on z of t, which was the modulating part of the drive, taking out the carrier frequency time dependence. That all has a prefactor of a voltage drive scale and the ratio of the drive voltage to the drive capacitance to the self-capacitance. There's a detuning term, J delta, where delta is the frequency difference between the resonator's resonance frequency and the carrier frequency omega. And then there's the decay term, which is written here, and again, involves QD. So this first order equation is really nice because it's easy to analyze what happens to this LC resonator when we drive it. So let's look at some examples. First of all, I'm going to take the case where the loaded Q from the drive is much, much greater than 1, and that's the case we work in superconducting qubits. So I'm actually not including this damping term or this decay term in any of the examples that I show right now. Suppose we turn the drive off, so z of t is equal to 0, but the detuning is not equal to 0. If we do that and we solve this equation, well, this first term is gone. There's no decay term, as we said, so we have phi dot is j delta times phi, and that's just a point rotating in the complex plane. So the trajectory is that the resonator goes around in a circle. And that simply means that the phase of the resonator is precessing in time, which makes sense because we've detuned it from the carrier. Now, what happens if we set the detuning to 0, but we turn the drive on and make it a constant? Well, in that case, the terms on the right here are all 0, and we have phi dot is just proportional to a constant, because like I said, we're making the drive a constant. And so if we start at 0, where the resonator is at rest, and we drive it, it just moves linearly in time away from the origin, where the phase, or the angle of the trajectory, depends on the phase of z. So if we drive with one phase, we get the blue arrow. If we 90-degree rotate the drive, we get the red arrow. Okay, now let's add an interesting wrinkle. What happens if we make the resonator nonlinear? And actually, this is the case for superconducting qubits, where we replace the linear inductor with a thing called a Josephson junction. Now that's a superconducting tunnel junction, which can be made in microfabrication process. And the interesting property of a Josephson junction is that their inductance is equal to a constant over the square root of 1 minus the current over the critical current squared, with a square root. So what that means is that the more current that goes through this junction, the higher the inductance gets. And so this is now a nonlinear resonator. If you drive the nonlinear resonator, rather than getting the straight line trajectories that we got before, we actually now get closed loops. So if we drive with the blue phase, the resonator starts to increase in magnitude like it did before, but now as we drive it, its frequency changes, and so it becomes detuned. And the detuning causes what was a straight line to turn into a bend. And the same thing happens if we drive with the red phase. It starts to go up, but then the detuning kicks in, and it goes around in a circle again. So that's what happens when you drive a nonlinear resonator. And it turns out that because our superconducting qubits are nonlinear resonators, this picture of closed loops in the IQ plane gives you a very good picture of how we control superconducting qubits, as I'll now explain. The important ingredient here is that once we cool down this resonator so that it's superconducting and quantum mechanical, the circle that I've been showing here in black, this circle, which is that constant energy, is one dynamical state of the resonator. In quantum mechanics, it turns out that physical states with a well-defined energy don't really have a phase. So this whole circle in the IQ plane collapses to a single point in the quantum mechanical case. But also the point at the origin with zero energy is a single point in quantum mechanics. So how can we interpret this? Well, what I've done here is I've taken the IQ plane and lifted it up so that we can sort of see it in 3 dimensions. And what you do is you take this circle with energy equal to h bar omega, and you collapse it in on itself by wrapping it around a sphere. So what happens is that this state with zero energy, which I label 0, gets mapped to the north pole of the sphere. And all of the points on this circle here, which I call the state with 1 unit of energy, I pull those around the sphere and I scrunch them down into the bottom point right here. As we do this, the trajectories that we had for a detuned or driven resonator also get mapped onto the sphere. So the green circle that went around and around the origin for the detuned case becomes a circle of constant latitude on our sphere. And the red and blue circles, which were the closed loops we got from driving our nonlinear resonator, get mapped into circles of constant longitude on the sphere. So here's the red one, and here's the blue one. This is really a faithful picture of what happens when we drive a nonlinear quantum circuit. The dynamical state of the circuit lives on the surface of a sphere, and we control the trajectories of that state by either detuning the circuit from the carrier or by driving it, where the drive phase is chosen to control the orientation of these longitudinal curves, these longitudinal red and blue circles. This sphere is called the Bloch sphere, and you'll see it all over the place in the context of quantum computing. You'll also hear some other terminology. Because detuning causes the trajectory to go around in circles around the z-axis in this sphere picture, we call those z-gates. And gates that rotate around the x or y-axes we call xy gates. And in the qubit case, rotating around the sphere from the 0 state around to the 1 state, that's just a not operation. It goes from 0 to 1, which is a state with 0 energy, to a state with 1 unit of quantum energy. Those 2 states are the 2 logical states of the qubit. All right, so now I hope you have an intuitive picture for the difference between a regular nonlinear driven resonator and a quantum nonlinear driven resonator. This circuit with the capacitor and a Josephson junction in parallel is called a transmon qubit. And that's what a lot of people in the field of superconducting quantum computing are using these days as their qubits. There are other types, but the transmon is probably the most common. Now that we have a good intuitive picture of how a nonlinear microwave resonator behaves at qubit, let's get into the details of how much microwave power we need to do logic gates and how much noise we can tolerate. All right, so here we're going to talk about the drive power that we need to do a NOT gate. Going back to the differential equation that we had describing this LC resonator, we can write down the case when there's a drive, a constant drive, but no detuning and no decay. And we get this equation here where phi dot is just proportional to the drive voltage. So let's ask, how much time and how much power do we need to get this thing to go from the 0 state to the 1 state? Now remember, the 0 state is at the north pole of this sphere, and the 1 state is at the south pole of the sphere. And when we drive, in the IQ plane, this nonlinear resonator goes around in circles. And on the block sphere picture, it goes in circles like this, about the x-axis or the y-axis. So we're going to be talking about a NOT gate, which goes from the 0 state to the 1 state, or the 1 state to the 0 state. In the quantum computing community, this is called a pi pulse. And it's called a pi pulse because we're talking about rotating by pi radians around the sphere. Okay, now the energy of this black circle that we mapped down to the 1 state on the block sphere is h bar omega naught, where omega naught is the resonance frequency of the qubit. But we also know that the energy of a resonator is 1/2 phi squared over L. So taking 1/2 phi squared over L and also bringing in the fact that we know what phi is after a certain amount of time from this equation, we can see that the total energy is this equation given here. So it's 1/8 CD over C squared times the drive voltage squared times T squared over L. And then now we need to relate that to the power. Well, the drive power, or I should say the available drive power, is given by this equation right here. So what's going on is that the available drive voltage is VD over 2. And then this equation is basically 1/2 V squared over R, where instead of R, I have the characteristic impedance of the transmission line that the drive is connected to. So if we take the bottom left equation for energy, the quantum equation for energy, and the definition of the available drive power and put them all together, we get the equation shown here. So the time to do this rotation from the 0 state to the 1 state is pi over 2. Pi over 2 is a prefactor that you can only get if you do the full quantum computation, but it's close to 1, so don't worry too much about it. And then we get this term that we get easily from the Kirchhoff laws arguments that I made on this slide. This equation makes sense. If the drive Q is larger, that means the drive is more weakly coupled to the resonator, so the time goes up. If the drive power is increased, then the time goes down. Putting in practical numbers, we typically want a gate time of about 20 nanoseconds, and we'd like the drive Q to be around 40 million, and so you get that you need an available drive power of around minus 75 dBm. Now, what about noise? Any drive voltage source also has noise, which we indicate right here. And the effect of the drive noise is going to be to make the qubit move randomly over the surface of the block sphere. And we can describe that random motion with a rate, gamma, where gamma is the characteristic rate and time of transitions from the 0 state to the 1 state and back caused by the noise. The formula for gamma is given here. You can find this formula using arguments similar to the ones I made in the previous slide. SA is the available noise power from the source at the qubit frequency. I'm sorry, I should have said it's the available noise spectral density at the qubit frequency. And QD and H bar are just as before. All right, so putting everything together, we have an equation that relates the gate time to the available drive power and the drive coupling Q. And then we also have a formula that relates the noisy transition rate gamma to the available noise spectral density and the drive coupling. Okay, so let's put in some numbers. Typically, the intrinsic quality factor of the qubit is around 1 million, and we'd like the drive coupling Q to be significantly larger so that the qubits Q is limited by internal effects and not from the drive. So typically we pick the drive coupling to be around 40 million. We want a gate time of about 20 nanoseconds and a noise transition rate that's significantly less than the gate time. So typically we pick something like 1 over a millisecond. Putting all the numbers together, we see that we need an available noise power of bigger than or equal to minus 76 dBm, and we need the noise power spectral density to be less than or equal to minus 204 dBm per hertz. That corresponds to a temperature of 300 millikelvin. This very low noise temperature is usually achieved by using a conventional source at room temperature and attenuating. The attenuators are inside the cryostat to reduce their noise to tolerable levels. Now, an alternative approach could be to put the signal source inside the cryostat, and that's an area of active research. Now let's zoom out and take a look at the whole system. So we've talked a bit about the qubit that goes on a quantum chip, and that chip is inside of a package that I'll talk about in just a moment. That package is connected through a bank of cables to the outside of the cryostat at room temperature, where we have our control hardware, that's our voltage sources and so forth. And then that's all controlled by a software stack. Now, some of the challenges involved in this system are listed here on the right. Commercial electronics are too expensive and too inflexible for our project, so we've had to make a lot of things ourselves, and that's an area where the microwave community has and will continue to make significant contributions. The controls all have to be synchronized, so each qubit has its own drive line, and they need to be phase matched to better than a nanosecond, so that takes some careful engineering. The cabling itself is expensive, it's heavy, and at this point, it's too big. So making denser cabling is going to be an area where the microwave community is going to have to make significant contributions in quantum computing. Furthermore, the packaging is currently at the limits of conventional technology, and I'll show some details about that in just a moment. Also, our on-chip wiring is a challenge. We have many wires on chip carrying microwave signals, and so doing the fan-out properly and keeping the crosstalk low is and will continue to be a challenge. Here are some pictures of our chip technology. So we use a flip chip technique where we have the control chip, and then that's bump bonded to the qubit chip that has the qubits on it. The control chip has input-output wiring. These two chips are bonded together through indium bump bonds, and we choose indium because it's both soft, making it suitable for bump bonding, and it's superconducting. In the bottom left are two electron micrographs showing the bump bonds. So here's just a zoom in of one of the bonds, and then on the right is a wire bond pad with a bump bond on the signal line and bump bonds on the ground plane on either side. In the top right picture, I'm showing a wider view of one of our chips. The squares are these indium bump bonds, and the railroad tracks are coplanar waveguides carrying the input-output signals. Zooming in on one of those coplanar waveguides, we see what's shown in the bottom right here. So this is a CPW, but it's got a lid over it, and the lid is done so that the crosstalk between neighboring lines can be kept low. Here's a picture of one of our flip chip devices. The black square in the center is the chip with the qubits on it. You can't see any features because they're on the other side. And then the big chip around it is the carrier with all the input-output wiring. So there are wire bond pads around the perimeter, and then you can see the fan out of all the lines going underneath the qubit chip to connect to the qubits. In this particular image, we have 156 bond pads at a 700 micron pitch. You can see that we're running out of wiring space. We've used up the perimeter of our carrier chip, and while we could continue to make the carrier bigger and bigger, that will eventually fail, and so we're going to have to find some way of bringing in more wires in a denser way on these chips. Here's a picture of the package. In the center is the bonded chips, and then around the outside is a 3-layer PCB. It's copper metal, but the front and back side are plated in aluminum to make them superconducting. We found that the ground planes need to be superconducting for good signal integrity. And that's actually still an area of research. We don't quite understand why that's the case. Shown in red are the wire bond pads, or I should say red indicates where the wire bonds themselves are. And then on the outside of the PCB is high density coax. These are actually PKZ connectors. So here's a more zoomed out picture. You can see the flip chip on the left with the package around, and then on the right side is zooming out even more with the package all assembled. So there's a magnetic shield that goes over the chip, and then PKZ connector banks that go around the outside with copper blocks to keep them mechanically stable. This is what it looks like inside the cryostat. So up here on the top, this round piece of copper is the coldest stage of our cryostat, and then vertically hanging down is just a copper mounting bracket to mechanically and thermally mount the package. And then here's the package with the magnetic shield and the qubit chip in the center and banks of PKZ connectors around the outside. This package has 156 input-output lines, and you can already start to see that while PKZ connectors are doing pretty well, especially compared to our old technology where we used SMA connectors and could only get up to about 28 lines, even now we're starting to be limited by the density of PKZs, and we're going to have to find a better way to improve the density of our microwave wiring. And that's an area where the microwave community can make very significant contributions to superconducting quantum computing. Here's a picture of our control electronics. There's a crate with slots for 14 boards, and we have two kinds of boards. I'm showing here the pulse generation board. It's FPGA controlled with 8 gigasample per second 14-bit DACs, and then those DACs go through onboard analog filtering to a front panel from which we take them to the sample. Here's another picture of the electronics. On the left, we have a crate stuffed with 2 boards, and then on the right, a crate stuffed with all 14 boards. There are 2 modules, 2 different kinds of modules in this particular crate. There's the DAC module that I already showed, and then there are also what we call mixer cards, and those are cards stuffed with IQ mixers and amplifiers that we use to bring the 1 gigasample per second signals from the DAC up to the 6 gigahertz needed to control the qubits. One of these crates can control 24 qubits, so it takes 3 to control a 72 qubit chip. And so you can already see that while this is dense enough to do experiments at the current scale, within a few years, we're going to have to significantly improve the density of our electronics. Here's a picture of the lab. This is a cryostat on the left side and 4 electronics racks on the right. 3 of those racks are stuffed with the electronic crates that I just showed. And these blue cables are carrying the microwave signals from the electronics into connector panels that go to the cryostat. So here you can really see that while this arrangement works for now, denser wiring is really going to be required for the future. This setup here is for 72 qubits. Once we go to thousands or tens of thousands, having these discrete coaxial cables is going to be completely impractical, and we're going to have a much denser wiring solution. This is a big opportunity for the microwave community. Now that we've talked about qubit control, let's talk about qubit readout. In this slide, I'm giving an oversimplified picture of how qubit readout works, and then we'll add some detail in the subsequent slides. The basic idea is contained in the circuit diagram in the top left here. We have a transmission line capacitively coupled to the transmon qubit, and we send a probe signal V in the transmission line. It reflects off of the capacitor and the transmon and comes back with a phase shift. Now, it turns out that the phase shift of the reflected wave depends on which logical state the transmon qubit was in, for a simple reason. As we discussed, the transmon is a nonlinear microwave resonator, so its resonance frequency depends on how much energy is in it. The energy is different for the 0 and the 1 states, as we talked about before. So depending on which state the qubit's in, its resonance frequency shifts, and so the reflected phase of the probe signal also shifts. We could view this whole picture in a phase plot as shown here in the top right. So here I'm plotting the phase of the reflected signal versus the frequency of the probe tone. For a single resonance circuit, the reflected phase goes through an S-shaped curve as shown here as we scan through the resonance. And because the resonance frequency depends on the qubit state, when the qubit goes to the 1 state, this S-curve shifts over to the left. The frequency shift between these two curves we call 2 chi, where chi is called the dispersive shift, and this whole measurement strategy is called dispersive readout. We probe in the middle of these two curves, of the two resonances, so that depending on which state the qubit is in, we get a large contrast in the reflected phase. We could also view this in the IQ plane. So here we have two clouds of points, blue for the qubit in the 0 state, one for the qubit in the 1 state. And you can see that they both sit on a circle, which makes sense because S11 lives on a circle when you're doing a reflection measurement, but they have a different phase for the reasons we just discussed. Now you can also see that these clouds have a big scatter. The scatter comes from noise, so let's talk about that. Okay, so in this slide we're going to explain the signal-to-noise ratio of the dispersive measurement scheme. So in the left here, I'm showing the two clouds of points, and they're separated around the circle, the S11 circle, by an angle theta. Now let's think about the noise level. We have the probe signal going in, it goes through a circulator, it bounces off the qubit, and then it goes out to an amplifier. Now it turns out that there's an amount of noise on the probe signal that you can never get rid of, and that noise has a spectral density of h bar omega over 2. This is called quantum noise, and it's something that you can never remove. It's required by nature. Similarly, there's no way to make a linear phase-preserving amplifier that has less than h bar omega over 2 added noise. That corresponds to a noise temperature of 0.1 Kelvin. This comes from actually basic principles of quantum mechanics, and so that basically means that you can never make an amplifier that doesn't double our system noise here. But still, that's okay as long as we can realize something with this low noise bound. And in fact, we can. Using a parametric amplifier circuit, which is pretty old technology, but now being done with superconducting materials, you actually can make amplifiers that saturate this noise bound at 0.1 Kelvin of added noise, which is great. Okay, so we have a certain power P of the probe signal. We have a measurement time tau. We have a noise spectral density S and an efficiency eta. So eta is basically what fraction of the energy manages to get to the amplifier. There's going to be some losses. The error in identifying these two clouds from one another, or distinguishing those two clouds from one another, is 1/2 complementary error function of the square root of SNR over 2, where SNR is equal to 4 times the sine of theta over 2 times the efficiency factor times power times time over the noise spectral density. Typical parameters are given in the bottom left of the slide. We usually use a power of minus 125 dBm, a time of around 300 nanoseconds, although we're trying to cut that down by about a factor of 2. Efficiencies range anywhere from 0.1 to around 0.4. It's very hard to do better than that. And the noise spectral density is typically 3 times 10 to the minus 24 joules. And that's coming usually from a combination of this input quantum noise and the quantum noise added by the parametric amplifier. Now, the paramp or parametric amplifier boosts the signal quite a bit, usually by 20 dB or so, but that's still not enough to be able to detect this minus 125 dBm signal. So we need another amplifier following the paramp, and usually that's in the cryostat, so it's a cryogenic LNA. Typically, it's a hemp-based amplifier, and those are great, but the commercial ones that we've been using dissipate too much power. We're running up to the point where they dissipate enough power that our cryostat can't keep them cold. So making cryogenic LNAs with a lower power consumption will be an important step for the future of superconducting quantum computing. All right, now some of the details. I said before that we couple this input line directly to the qubit, but that's not quite true for the following reason. This capacitor here determines how fast you can couple the readout signal into and out of the qubit, but it also determines how fast the qubit's own energy leaks out into the readout line. So that's bad because it means that the time it takes us to do readout and the time that the qubit survives in its excited state before falling down to its ground state are the same time. That's not good because if the qubit has a high probability of decaying during the measurement process, then the measurement's not going to be very good. So what we do to fix this is we add another resonance to the circuit. So here we've added a linear resonator in between the input-output line and the qubit itself. And it works like this. The resonator is at a frequency omega r, as shown here, and the qubit is detuned by a large amount here at omega q. Usually this detuning is a gigahertz or 1.5 gigahertz. So what happens is that because the qubit and the resonator here are coupled to each other, as the qubit changes from one state to another and its resonance frequency changes, the resonance frequency of this resonator also changes. So that's represented here by the blue and red curves. So these are the same phase curves that I showed before, but now they're up at the readout resonator's frequency while the qubit's way down here. So this is good. The separation of frequencies is what we need because now we can couple the readout resonator strongly to the input-output line so that we can measure quickly. But because they're at different frequencies, what happens is that from the point of view of the qubit, this resonator looks like a short to ground. So the qubit can't easily lose its energy out the readout line. And that's how dispersive readout actually works. We have a readout resonator detuned from the qubit, we couple strongly to the readout resonator, and then we couple the readout resonator and the qubit to each other, but we keep these two at different frequencies. In fact, it turns out that one extra resonance isn't enough. We use two. Typical jargon in the field is to call this first resonator the readout resonator, and then we have another one here called a Purcell filter. The name Purcell filter is historical, but the point is that by having two resonances here, we can greatly separate the timescales of the qubit's energy leaking out the readout line and the time it takes to actually do readout. With an arrangement like this shown to the left, there's a constant that you can write down, which is kappa, and that's the ring up time of the readout resonator, and T1. T1 is the time that the qubit lives before losing its energy out the readout line. The product of those two is bounded by the readout circuit by this formula. Delta is the detuning between the between the readout resonator and the Purcell filter. G is how strongly the qubit is coupled to the readout resonator. Omega q is the qubit frequency, and QF is the loaded quality factor of the filter. And so when you put this all together, you find that this first term is what you're getting just from the readout resonator, and this second term here is what you get by adding the Purcell filter. The Purcell filter term is usually in the order of 80 to 100, so it really makes a big difference. It lets you make this constant about 100 times bigger, which you could interpret as saying that for a given readout speed, you can make the qubit live 100 times longer. All of the devices we make at Google use dispersive readout with a Purcell filter, so now you know the basic idea of how a readout works. Okay, so now the conclusions. In the first part of the talk, we saw how superconducting qubits can be thought of as nonlinear microwave resonators. So that sort of sets the context for why the microwave community could be interested in and could really do a lot of work in this field. And then I tried to give an idea of where the opportunities for the microwave community to make contributions are. So here are a few of them. A big one would be denser wiring from room temperature to the chip package. Another one would be a higher density of connections on the package and to the chip itself. And of course, in all of those challenges, keeping the crosstalk low is paramount. We also need to have increased density and lower power consumption of our control electronics. You saw those photographs with 3 or 4 racks of electronics just to control a 72 qubit chip. So as we go to thousands and tens of thousands, we're going to have to make those electronics much denser. And then at the end, I mentioned that lower power cryogenic amplifiers are going to be necessary so that we can make a larger scale system and still keep the whole thing cold. Thank you very much for your time, and I look forward to answering your questions.